this lecture, we look at direct sum decompositions in greater generality than we did in the previous lecture. So now suppose M is an R module. We say that M is the direct sum M1, M2, Mk if firstly Mi is a submodule of M. For every I, let's say every I between 1 and k. And secondly, for every element M of M, there exist unique elements M1, M2, Mk with Mi belonging to Mi for I between 1 and k, such that M is equal to M1 plus M2 plus Mk. So this is similar to the decomposition into two parts, but there we also had this condition that M1 intersect M2 is trivial, being equivalent to the uniqueness. And in this case, what this means is that if you take Mi and intersect it with the sum of all the other modules except I, then this will be 0 for every I in between 1 and q. So that's the analog of the intersection 0 condition. But in any case, what we are saying is that M has a unique decomposition. So you should try as an exercise to prove that the uniqueness of this decomposition is equivalent to this. And the proof is quite similar to the proof in the case where we just had a decomposition into two submodules. Okay, and now we can do the calculus of projections in greater generality. So again, you define Pi from M to M by Pi of M is equal to Mi when M has decomposition M1 plus Mk with Mi belongs to Mi for 1 less than or equal to I less than or equal to k. And of course this is well defined because these mi's are uniquely determined by M. And once again we have the following conditions. The identity element of M is P1 plus P2 plus Pk. We have Pi squared equals Pi for every I, and then we have Pi Pj equals 0 for all I not equal to j between 1 and k. And also we have that Pi belongs to the R module homomorphisms from M to M, which is a ring which we are denoting by end Rm. So all these things up here are happening inside this ring end Rm. It turns out that this calculus of projections is actually equivalent to direct sum decomposition. So conversely, let's call these conditions collectively star. Okay, now conversely, suppose we have elements P1, P2, Pk belonging to end Rm satisfying star. Okay, so I just have a module M and I give you elements P1, P2, Pk, which add up to the identity. Each Pi is its own square, which in other words means that Pi is an idempotent. Pi Pj is 0 for I not equal to j. So this is called the orthogonality condition. So this is orthogonality. This is the idempotence condition. And this condition is sometimes called partition of unity. Okay. Suppose we have P1, P2, Pk satisfying these three conditions. Then define Mi to be the image of Pi. Then we have M is M1 plus Mk. And this again is not very difficult to prove. The fact that Mi is actually a submodule follows from the fact that Pi is an R module homomorphism. So that's not very difficult. And then the fact that each M can be written uniquely as a sum of M1 plus M2 will follow from the other axioms, the other three axioms. That is partition of unity, idempotence, and orthogonality. It's a very nice exercise which I strongly recommend that you all try out. Okay, so let's look at an example of this partition of unity. Let's take R to be M and K, and where K is a field. And R is a left R module. And let EI be the matrix with 1 in the ith place and 0 everywhere else. So for example, if n equals 2, I'll have E1 is the matrix 1, 0, 0, 0. E2 is the matrix 0, 0, 0, 1. Right? In general, you'll have these for 1 less than or equal to I less than or equal to n. Then what we have is the identity homomorphism of M. Okay, so what we'll do is we'll define Pi of A. So Pi is from MnK to MnK. It's supposed to be an R module homomorphism. So let's just define this to be AEI. Then P1 plus Pn of A is AE1 plus En, which is A times identity, because E1, E2, En add up to the identity matrix, which is the identity of MnK, identity of R as a left R module. Also, it's easy to see that each Pi is an R module homomorphism. And so these Pi's form partition of unity and their idempotence and their orthogonal. This is identity R of A. So it satisfies all those conditions on the previous page, which I collectively called star. And what is Mi in this case? So it turns out that Mi is all matrices with non-zero entries only in the ith column, or um, all entries outside the ith column are zero. And indeed, you can see that R will be a direct sum of these submodules. So for example, in the 2 by 2 case, we have M2K is the direct sum of matrices with non-zero entries in the first column and matrices with non-zero entries in the second column. And these are actually left R submodules of M2K.